This is Endeavor. And this. And this. Give it a second. Is Endeavor 2. I got it wired up and running on some basic firmware that allows for teleoperation from a Bluetooth game controller. In this video, I'm going over how I did it. Let's start with a rough wiring diagram. As mentioned before, the controls are done by an ESP32 to handle the Bluetooth controller, and the Camargue Servo2040 to handle the servo control. Both boards communicate with each other over the UART protocol through the transmit and receive wires. The ESP32 also controls a relay that toggles power to the Servo2040's high power input. Next, here are the power paths. Common ground is connected to all components. A rocker switch is added to toggle power to the rest of the system, and the switch's output routes to the relay common pin, 5-volt buck converter, and segmented display voltmeter. The 5 volts from the buck power the ESP32, Servo2040, and relay. Overall, the electronics layout is nothing too special, and doesn't change from the original version, aside from the rocker switch. However, before I start wiring, let's revisit the firmware I wrote for the original design, since it's convenient to test things out before the two microcontrollers are stuffed inside the torso. Here's a visual representation of the original code, since the code itself is a mess. The ESP32 firmware was built from a boilerplate example provided by the BluePath32 library. The boilerplate connects to any controller, but with a few lines of code you can set up an allow list that exclusively pairs the robot to your personal device, given that you have its MAC address. The control structure is straightforward. The ESP32 waits for the controller to connect, after which the main process periodically retrieves input data from the controller. If a button or joystick is detected, the ESP32 sends a single character byte to the Servo2040 to indicate the button being pressed. The Servo2040 follows a similar control structure. If the UART buffer receives a character byte that matches, the board will execute the servo sequence for it. B to crouch, W to walk forward, and so forth. Seems easy enough. Well, there are a few problems with the setup. First and foremost, there is no clearly defined central control unit. Both boards have similar control structures, and both carry a role in the primary functions of the robot. Because of this, there are times in which both boards need to be modified to add new functions or update old ones, and this is problematic because the Servo2040 especially is a whole process to update firmware. Meanwhile, on the Arduino IDE, the ESP32 can be flashed with the click of a button. Inconveniences aside, the second problem was with the UART messaging protocol. Sending single character bytes to indicate fixed motion sequences is very rigid, and it does not translate well to the dynamic and fine control that I'd like to explore later down the line. UART can be used to process a lot more data quickly, and this was a very simplistic utilization. That was old Endeavor firmware. For this new version, I rewrote the code to improve upon these issues. Mentally, I designated the ESP32 as the central control unit, responsible for processing both the Bluetooth controller and the servo sequences, whereas the Servo2040 is a client device that can set each servo individually based on UART messages. So to kick off the rewrite process, I sketched out a communication protocol to identify how messages are formatted and processed on both ends. By default, UART messages are sent in bytes, which contain 8 bits representing a value of 1 or 0. I decided that the first byte of a message sent from the ESP32 to the Servo2040 is the command byte, in which the first 4 bits are a preamble. For now there are 2 possible preambles, no return and return sensor data. This serves as a verification that the message is valid, and also tells the Servo2040 whether to send back data from its built-in current and voltage sensors. The remaining 4 bits is a command code, and there are 5 different codes: set pulse with delay, set LED, enable, and disable. Depending on the command, additional argument bytes will be sent. Enable and disable signify whether PWM signals shall be transmitted to the servos and do not take additional information. The LED command takes 1 argument byte. The first 6 bits, starting from the right, indicate one of 6 LEDs built into the Servo2040, and a 1 or 0 indicates on or off respectively. Set pulse takes 36 argument bytes total, 2 bytes per servo starting from servo 1 up to servo 18. Conjoining the byte pair's decimal values will give the pulse value in microseconds to be set. If only a few servos need to move, then I've made it so that only values within the servo's allowable range are acknowledged. There is also set pulse width delay, which adds another argument byte pair to indicate a time delay in milliseconds for the servo to arrive at a target position. With the command protocol drafted, I went ahead and wrote firmware for the Servo2040 to process these commands. I then tested this using an Arduino Nano that transmits these commands over the UART wires. The first test was to index the LEDs on the 2040. This was the first function to be added to make sure my implementation of the protocol was correct. Next, I hooked up some small servos and wrote a simple sweep sequence. This more or less marked the completion of the firmware for the Servo2040. Overall, I'm very satisfied with what I wrote. I hardly need to reflash the board unless I'm making new additions to the protocol or applying bug fixes, which means most of the programming work can be done on the ESP32. Furthermore, because the new protocol allows for direct servo control, I can look into dynamic movements that aren't reliant on a fixed motion sequence. But with that, we're ready to work on the electronics so we can develop the ESP32 firmware with the full robot. Let's get to the wiring. Okay, at this point I stopped recording to fix a few things. Since then I've routed and tidied all of these servo cables. It's a lot tighter this time around, and while it's still a jumbled mess when opening up the back cover, at least the torso internals are pretty clean, which makes it significantly easier in the case I need to do some maintenance inside. The battery slots in from the top, and flicking the switch shows that everything has been wired up properly by the fact that no magic smoke is coming out. Now all that's left to do is write the ESP32 firmware. I wrote the ESP32 code on the Arduino IDE. It's not as ideal as something like Platform I/O, but it gets the job done. Before we can start actuating the servos, we need to add the calibration values from the previous video. I wrote down each servo's middle, minimum, and maximum pulses, and I created a C structure to contain these values in code. There's also a Boolean value to distinguish between 180 and 270-degree servos for the 5 of the latter that are mixed in. I have 17 structures defined, one for each servo. Then I made an array named servo cluster, which tracks these structures in the order of their physical pin mapping on the Servo2040 board. This is so that the calibrated angle to pulse mapping will pull the correct values when indexing through each servo. Next, let's look at some of the commands that are commonly used. Send command takes in the preamble and command code as parameters, using bitwise operators to form the command byte that can be sent over UART. The preambles and command codes are defined as constants in the header file. Set servo cluster sets the servos to the angles provided in the angles array. The pin mask parameter is an 18-bit binary that represents which servos are to be actuated. The least significant bit corresponds to servo 1, and the 18th bit is servo 18. If the bit is a 1, that indicates that the servo is set to an angle within the array read left to right. If the bit is 0, then the servo is set to an arbitrary value, which according to the command protocol is ignored by the Servo2040. Set servo sequence is specifically built for looping sequences containing multiple keyframes. It takes a sequence array, sequence length for the number of elements within the array, the pin mask, and an indexing parameter that indicates the keyframe for the robot to pose at. The function can be placed in a loop with a time delay and increments on the indexer integer to animate the sequence on loop. These are more or less the building blocks for the action functions that make the robot move depending on the buttons being pressed. As to how the servo angles and sequences were made, static poses or animations that have very few keyframes were done using some rough storyboarding and posing of the unpowered robot, and estimating the angle for each joint. As for the walking sequence, I used the Python inverse kinematic solver that I showed in my first video. I intended on phasing this out to explore pre-built tools designed specifically for robotics, but for basic leg control this still has its uses. That first video will tell most of what you need to know, and the code is on the GitHub repository if you want to have a closer look. I use this to generate a majority of the leg motions for Endeavor 2, using print functions to output the servo angles in a format that can be copy-pasted into the sequence arrays of the ESP32. The walking gait's parameters did have to be adjusted from their original values because the leg height and weight distribution changed with the new design, especially with the addition of the heavier battery. This was a trial and error process once again to optimize the parameters until a stable walking gait was achieved. I do wish I was at the level of integrating some form of machine learning to expedite this process, but regardless, I've completed all the motions that I wanted to add to Endeavor 2. So with that, let's take our robot for a test drive. And there you have it, basic firmware for a remote-controlled humanoid robot. The robot is able to move around, do some combat moves, and perform a front roll as a finisher move. I even got an emote wheel on the D-pad. Low-key, the best feature I've added. Overall, I'm very happy with how the project is going. I've checked off most of my goals for the rebuild, although there are a few issues remaining. These single-ended joints still tend to come loose over time. It's less noticeable with the steel ball supports and Loctite on the hub screw, but I may need to look into this again or accept that some occasional maintenance will be needed. Also, I'm starting to see why humanoid robots do not use geared actuators. The backlash on these joints are not ideal, and this can only get worse as the internal gears wear down over time. It could also be the fact that these are hobby RC servos and not robot servos, so precision may not be as important in the actuator design. Perhaps a new robot with robot servos or even brushless motors may be in the pipeline someday. But in any case, I'm working with Endeavor 2 for the foreseeable future. I have many plans for this robot, but I think the next phase of the project will be to implement dynamic balancing. One limitation of a fixed walk sequence is that there is no means to compensate for external forces or changes in terrain. By implementing some form of feedback control with the help of an inertial measurement unit, I'm hoping to make this robot more than just an expensive remote control toy. Alright, that should do it for this video. I'm really excited for what's to come for Endeavor 2. I'm not well versed in things like controls and software, but learning as I go has been my motto since initiating the project a year ago, so I guess this is where the fun begins. The code I featured in this video has been uploaded to the GitHub repository, and I expect the CAD model to come sometime in April. I'll also be working on some documentation for assembly and instructions, so keep on the lookout for that. If you enjoyed this video and wish to be in the loop with my projects, I would appreciate it if you can hit the like and subscribe button. Thanks for watching, and I'll see you next time.